Fault sets are an optional feature of ScaleIO that allow an administrator to manage system availability at data center scale. In a system configured with fault sets, ScaleIO can continue serving data if an entire rack or chassis fails. Let's start with an example. The ScaleIO administrator defined fault sets at the rack level because of environmental considerations such as limited power or network redundancy. Fault sets provide units of redundancy. They do this by placing physical constraints around where redundant data copies can be held. As data chunks are written to the system, the primary and secondary copies are placed in different fault sets. This means that if an entire rack fails, redundant copies will still be available inside other fault sets. Since this system was configured with rack-level fault sets as the unit of redundancy, I/O can continue as the remaining nodes work in parallel to rebuild data protection. Once data protection has been rebuilt, the system will be in a state where it can survive the loss of another rack and rebuild again if there is sufficient free space. In addition to providing rack-level redundancy, fault sets can also be used to protect against chassis failure when third-party blade servers are used. Fault sets can also be used to place all the nodes in a rack or chassis in maintenance mode for planned operations. If you're already familiar with ScaleIO, you probably noticed that a system with fault sets behaves a lot like a system without fault sets. The difference is that a system without fault sets protects data by mirroring it on different physical nodes. A system with fault sets, however, places mirrored data in different fault sets. In this example, that means that the mirrored data copies shown here would have instead been placed in different fault sets. This is because in a system without fault sets, the unit of redundancy is a node, but in a system with fault sets, the unit of redundancy is a group of nodes. Fault sets are defined inside protection domains. A protection domain establishes the boundaries where data copies are maintained. A ScaleIO system can have multiple protection domains. Each protection domain can have multiple fault sets. When a system is configured with multiple protection domains and fault sets, the system can recover when fault sets in different protection domains fail at the same time. In this configuration, ScaleIO can continue serving data when 40 nodes are lost at once. Today, we will show a scaled-down demo where 2 nodes fail at once. We'll be working today with an 8-node ScaleIO system consisting of Dell PowerEdge 13Gs. All the nodes reside in a single protection domain, Protection Domain 1. There are 4 fault sets with 2 nodes each, fault sets A, B, C, and D. Each node is using 2 10 gigabit Ethernet ports, and each node has 6 SSDs and 18 spinning disks. On this system, all the SSDs are in one storage pool, and all the spinning disks are in another. A storage pool is an elastic, software-defined collection of physical drives that holds user data. If you're new to ScaleIO, consider watching our video on storage pools after you finish this video. With the system under load, we will simulate a rack or chassis failure by halting the hypervisors on 2 of the nodes at once. Within a few seconds, the remaining nodes in the system will begin a rebuild operation to re-establish data protection. Once the rebuild operation is complete, we will examine the state of the system and we'll wrap up. Here we see the ScaleIO landing page. The ScaleIO system has more than 190 terabytes of raw capacity and is servicing a workload consisting of both reads and writes. The system has a total of 191 drives consisting of a mix of both SSDs and spinning media distributed across 8 nodes. As we showed in the visualization, all 8 nodes are inside the same protection domain, Protection Domain 1. Here we can see each of the 8 Dell PowerEdge 13G nodes that make up the cluster. Notice that the system is divided into 4 fault sets consisting of 2 nodes each. In production, each fault set would likely contain all of the nodes in a given rack, or if third-party servers are used, each fault set might contain all of the nodes in a given blade chassis. As you can see, the I/O load and the capacity are evenly distributed among all the nodes in this protection domain. If you're interested in understanding ScaleIO's even I/O and capacity distribution, consider watching our video on storage pools after you finish this video. Today we will illustrate how ScaleIO can continue serving data even when all of the nodes in a fault set are lost at the same time. We will do this by simulating an unplanned failure that takes down multiple nodes at once. We will do this by halting the hypervisors running on the first two nodes. After the nodes go down, ScaleIO will begin redirecting user I/O to the surviving nodes, and a parallel rebuild operation will begin among the nodes that make up the surviving fault sets. We have now halted both of the nodes in the first fault set. This video segment is displayed in real time to show the speed with which ScaleIO identifies the failure, redirects user I/O, and begins the parallel rebuild operation. The I/O has now ramped back up after the ScaleIO cluster redirected the clients to the locations containing redundant data chunks. On the right, the system displays the rebuild activity that occurs as redundancy is reestablished. The nodes all work in parallel to reestablish the redundancy, but as before, redundant data chunks will not be placed inside the same fault set. We will now wait for the rebuild operation to complete. The rebuild is complete. The user I/O continued despite the loss of the fault set. A rebalance operation has evenly distributed the load and capacity across all the surviving members. When the nodes in this fault set are brought back online, the system will rebalance again to make use of all the available capacity. Fault sets can also be used to facilitate planned operations that involve groups of servers by allowing the administrator to place multiple nodes in maintenance mode at the same time. Note that in order to achieve the benefits of fault sets, the system must have enough free space to rebuild the storage pools in the surviving fault sets. This is why fault sets are an optional feature of ScaleIO. In many deployments, protection domains configured without fault sets are sufficient. Also note that if fault sets are used, a minimum of 3 fault sets must be defined. Let's wrap up and review the fundamentals of ScaleIO fault sets. Fault sets control units of redundancy inside a protection domain. By default, ScaleIO's mesh mirroring layout works across nodes. When fault sets are defined, ScaleIO's mirrored layout works across fault sets. Fault sets provide resiliency against multiple nodes in a protection domain going down at once. They do this by grouping nodes that are likely to experience a failure together. Fault sets can be used to provide rack-level redundancy in cases where power or network redundancy is an issue. Finally, fault sets can provide chassis-level redundancy when blade servers are in use. ScaleIO fault sets allow an administrator to manage system availability at data center scale. They bring hardware and location-aware redundancy to enterprise-grade software-defined storage.